Hey guys, today we're going to be going through recurrence relation and solving 3 problems that demonstrate this property. So the first problem we're going to solve is reverse a linked list, and it's a pretty straightforward problem. All we have to do is turn the linked list completely around, but there are some challenges to this. So I will type out the problem and then talk about it as I go. Alright, so this is the basics of how the recursive function is set up. And here is the base case for the recursive function, and here is the recursive call. And we'll be doing all of the functionality of switching the order of the list as the recursive function unwinds. Alright, so this is the completed function. As you can see, we don't really do anything as the recursive function winds up, but we do a lot as it unwinds. So all of the functionality is after it's already made it all the way through the function calls and then hits the base case and then starts unwinding. So I'll run this code. Alright, so it seems like I had a little typo. So I'll fix that, then run the code, and as you can see it passes. Then I'll take this out just for the submission. I'll submit it, and as you can see it's accepted across all of them. So I'll run it again just to show you what it does. Alright, so these 2 lines are where the bulk of the functionality in reversing the linked list actually is. The rest of the lines are just the base case and making the recursive calls and returning it. So let's go through what these 2 lines are doing to reverse the linked list in this problem with an array of 1, 2, 3, 4, 5. Alright, so we make recursive calls all the way down to the base case, which in this case we would be at 4, and then we check if node.next is null. It's not, so then we go to 5. Node.next is null, so then we return node, break out of this recursive call, and now we're on 4 again, and we say, alright, node.next equals node. So right here we have node.next, so after the 5, is equal to 4. And then in this scenario, 4 would be pointing to 5, 5 would be pointing to 4. So then we have to undo 4 pointing to 5 by saying node.next is then equal to null. So now we sort of have 2 separate linked lists with 1, 2, 3, 4 and 5, 4, which we just made right there. And then we return reverse list and move on to the next one. So now we have 1, 2, 3, 4 as our first list, and then we have 5, 4 as our next one. And we just repeat the process. So we say node.next, so it's after 4 is 3, and then we separate that from 3 by saying node.next is equal to null. And we keep on going through that until we reach the end of it where we return 5, 4, 3, 2, 1. And you can kind of see how this works right here. So this is just showing the reverse list, which is what we return. And what I'm talking about, how we have 5, 4, 5, 4, 3, 5, 4, 3, 2, and 5, 4, 3, 2, 1 finally. And once we get there, we're all the way unwinded out of the recursive calls, and we finally return switch list head. Alright, so now on to the next problem. Search in a binary tree. So all that we're trying to do in this problem is find the node that matches val and then return the tree from val. And we do this in a recursive manner because this is recurrence relation. So I'll reset my code, and again I will type this out and talk about it as I go. Alright, so here's the basic setup of the recursive function, and I'm using a value called found just to check if we have in fact found the node that is equivalent to val. And this will just help us out when we unwind the recursive call so that we don't have to constantly keep checking if the parent node is equal to val. Alright, so right here is our base case, and we say if node.val is equal to val, then found is equal to node, and that's what we'll be returning right here. And then we return to break out of that recursive function. And here are our two recursive calls. So as you can see, if this dot left, this dot right, so we have two possible places that we can search. So if node dot left, then we call the recursive function on node left, and same with node right. And then finally, I add this line right here, which just says if found, just return, break out of the function, because once we reach the base case, we don't need any of this stuff. So I'll run the code, and as you can see, it returns properly. So I will go through how this is working with this right here, with val2. So what we do is we enter right here with for, as we call, search root, and then we check, here I'll switch this, just so that we can, alright, so we call it with search root, we go through, it checks if node.val is equal to val, it is not because we're looking for 2, then it goes through, checks if node right is not null, and it is not, so then we go down, 7, right there, it's not equal to val, and node right is null, node left is null as well. So then we break out into the original recursive call, which stopped right here, and then we check if node left. So then we search node left is equal to node.val. So then we console log it just to check, and then we set found to equal to node, and then we break out of this function. And then we're in the base function, it finished all the way through, and then we just return found right there. But if there were more, let's say that this is 2 right here, and then we still have the left one to search, anytime that we would go deeper into the tree, it would just call this function, check if found, and then it would just return to make it faster, I guess. Alright, so now let's explore the last of the 3 problems, Pascal's triangle 2, which Pascal's triangle is just this, which is demonstrated right here, and all we have to do is get a number and then return what the row is at that index. So this is row 0, this is row 1, this is row 2, and this is row 3. So we get that number 3, and we have to return something like that. So I will reset, and I will type this out and then talk about it as I go, as always. Alright, so here is the recursive function that we're going to call, and here's the base case. So as you see, as I'll type more, I'm going to increment index, and once that is equal to row index, which is this number that is provided to us, then I will return the prev row, which is also another variable that we will pass into triangle. So we start out with triangle, and we pass it 0 and an array that just has 1 in it, because as we see right here, at the 0th index, we just have an array of 1. Alright, so here's the frame of what we're going to be doing to manipulate new row. So as you see, we push 1 into new row. We're going to put a for loop right here, and then we push 1 again into new row, and then we recursively call triangle with index incremented, and we pass new row, which will become prev row in the recursive call. And we push 1 twice into it like that, because as you can see, on every single row of Pascal's triangle, there is 1 at the start and 1 at the end. So now I'll type out the for loop, and that is how we add these numbers in right there. Alright, so here's the for loop that adds all of these middle numbers into Pascal's triangle. And as you can see, all we're doing is just pushing prev row I plus prev row I plus 1. And you can see what's going on right here. So we have prev row I and I plus 1, so 0 and 1 add together, push it after the one that we pushed before the loop, so we get 3, and then we push 1 and 2, or index 1 and 2, I guess it's kind of confusing, to get 3 again, and then we push another 1 right there, set it as the new prev row, move on to the next one, push the 1 to it, and then we push index 0 plus index 1, which is 1 and 3, to make 4 right there. We move on here, then there, and then we finally push the last one. And we can do this as many times as we want to until we reach where index is equal to row index. So I'll run this code. As you can see right there, the answer is equal to the expected answer. Submit it, and it's accepted. So that is 3 examples of recurrence relation. I hope you enjoyed. Thanks for watching. Be sure to like and subscribe. Have a good one.